Hi everyone, and welcome to our video on a word problem involving uninhibited population growth. Okay, so we've got this setup where if they give us a derivative, so the differential equation, so this is a derivative equal to something, or the derivative still equal to something like this, where we have a constant times another function, then we can rewrite it right away. So in our format, let's box this one up, and there's the arrow there. So this models a population growth. And when we have this derivative equal to kp, we can instantly convert it to a full function, so not a derivative, so an original function, where we have this exponential form. Okay, where p naught, so this thing, so they call that knot, like K-N-O-T, like a shoelace knot, represents the initial population. And sometimes you might see it a little different. They might do like capital A equals P e to the RT, so something like this. But this P is still that same P naught. They might change the left to be capital A for like an amount, and then R instead of K just to mix it up. So they might change the letters, but it's always this format. All right, so most of these problems do require a calculator, so I do have Desmos ready, but let's make sure we can set everything up. So it says a city has a population of 10,000 in 2020, and the expected growth rate is 4% per year, which means, so they give it to us also in this way, which means we have this derivative dn dt equals 0.04n. Find the function that satisfies this equation. All right, so let's rewrite this dn dt equals 0.04n, and we'll do what we did in the last video to rewrite this. So we know that this capital N will be by itself, and then equal to some constant times e to this 0.04, and then whatever the other variable is, which is t in this problem. Okay, and then what we're going to do is clean it up. Okay, so I notice I didn't follow the exact same form that I just boxed. I was following the form from these ones that we saw from a different video. Okay, but just to show it still works the same way, again, just the letters are changing. So what we're going to do on the left is say, well, this should really be n of t as a function. And then they say a city has a population of 10,000. That's the initial amount. That's the initial population. So I'm just going to say initial, which means that's where this should go. So it should be 10,000 e to the 0.04 t. Okay, so I notice the 4% matches the 0.04. Okay, so they like to mix the notations around, but they mean the same things. Okay, so this is the function. And we ran a little low, but that is the function. And then it asks, what will the population be in 2030? Okay, so in these scenarios, when they say the initial population was 10,000 in 2020, that does mean for t equals 0, it represents the year 2020. And so, and back and forth, both ways. And so what they're asking for, so for what will the population be in 2030? Well, that's 10 more years after 2030, or after 2020, sorry. So we should have 10 for our t. Okay, so that's how they usually break it down. So for a year in our, like, I guess calendar year, so 2020, usually we don't use that number. We like to say some initial point matches with t equals 0 for it, and then from there we continue counting. Okay, so 2030 is 10 more years than 2020. That's why we will use t equals 10. Okay, and so we'll just plug that in. So now that we've got it, they're just saying, hey, do n of 10, which equals 10,000 e, and 0.04, and then change the t to 10. So I'm just using the same equation there on the left, the same function. And then now is where I need a calculator. So we have n of 10 is equal to, okay, so I've got Desmos, and I'm just going to type it in exactly the same way. Now, you might need to, depending on if you have a handheld calculator, use these parentheses as well to make sure that the power is all in the power instead of like a different, so the calculators might not read it the same way. Okay, but I'm going to just type that in, 10,000 E, and I'm going to use my parentheses now, 0.04 times 10. There we go. Okay, so I'm using the parentheses, and I did times instead of multiple parentheses, but it's the same thing. Okay, and then we'll just round it to the nearest whole number, so 14,918. Okay, so we have 14,918. Okay, so that's the population 10 years from 2020. Okay, so almost 5,000 more. Okay, so let's see this next one, 3. It says estimate the rate of change in the population in 2030. All right, so rate of change, that's back to saying, hey, do a derivative. So we're going to take our function that we found from step 1, the n of t equals 10,000 e to the 0.04 t, and then we're going to do its derivative. So n prime of t is, again, the exponential function's derivative is itself, so 10,000 e to the 0.04 t times the derivative of the power, which would be 0.04. Okay, and here we can simplify if we need to, but I'm going to plug in, so it says in 2030, so now I'm going to let t equal 10 again, and do n prime of 10 equals 10,000 e to the 0.04 times 10, and then after that times 0.04. Okay, so I'm just doing it in one big step instead of simplifying because I need a number anyway. And so look at this, I already have that. Same thing ready to go, but I just need to multiply it by 0.04. There we go. Okay, so we get 500. Again, let's round it to the nearest whole number, so we'll do 597. Okay, so we have n prime of t equals 597. And so what that means is the population is increasing because that's a positive number. Population is increasing at a rate of 597. I'm going to assume people. Okay, so it says a city has a population. They didn't say people, but let's assume that, right? So population is increasing at a rate of 597 people per year at year 10. Or at, let's just say at 2030. At the year 2030. Instead of at, I was going to say year 10, but that really means 10 years from 2020. So let's just say 2030. Okay, so that's what that means if they need us to interpret the results. Okay, but that's that. That's how we can break down these problems. We'll do a couple more examples, but for now, that's it. Thanks for watching, and I'll see you again soon.